Happy birthday to you. Happy birthday to you. Happy birthday, dear V. Happy birthday to you.
We should make a choir.
I know, that was pretty good, right?
I mean, we got 5 of us.
Doesn't that explain why you're not in choir?
Somebody take out a piece of paper and have everybody sign their name on it.
Pretty good.
And while you're passing that around, couple of questions. Just in time, where the attendance quiz is going around. Ann Arbor people automatically get grandfathered in as present, I suppose.
So I just have them comment on the YouTube video.
Well,
There you go. You can tell if they watched it or not.
I think it'll be okay. So, a couple things I want to address, and then we'll do the homework assignment. So one of the, from the survey that went out the other day, one of the things that a lot of folks pointed out is that they spend a lot more time on the homework in this class than they do in other classes. So let's talk about that for a few minutes. For starters, how many of you are CS majors? All right, so all hands. And I assume that's probably true for the
I'm Zumba.
Ann Arbor people as well. Now, how many of you are taking a gen ed class like psychology, sociology, something else like that, some other non-CS class this semester, right? And I presume that you're probably spending a lot more time on your 470 work than you're spending on that class, right?
Kind of both.
If you're finishing your 470 work, you're probably spending a lot more time on, this homework takes a long time, right? It's tough. How many of you have heard the rule of 10,000 before? We have this thing called rule of 10,000. This says it takes 10,000 hours to master I'm just going to call it a subject. We can say master something. Now let's just presume everybody in here is in a psychology class. Just picking on them for no reason. This isn't an anti-psychology thing. It's a pro-CS thing because that's what your majors are going to be. Having said that, would you want to spend 10,000 hours on psychology? That's probably why you picked computer science as your major, right? Now, so to flip it around, do you want to become a master in computer science so you can excel in your vocation? Maybe make some sense. You're paying a lot of money for tuition, right? So you probably want to get as much out of that as possible. Is that a fair statement? I mean, we could sit here and argue about why you shouldn't always take 18 credits. You're paying for it. You might as well get the best deal you possibly can, right? Sleep later. So sleep when you're older. So punchline is that when you're, and we talked about this before with one of the assignments where, if you hit a wall, this was a couple assignments ago, I think, if you hit a wall and learning's no longer taking place, well, that doesn't count as your 10,000 hours, right? That's, 10,000 hours is practice that is productive, constructive practice. Not necessarily high performance practice, but constructive practice. So when you hit a wall, sometimes you need to get a little nudge in the right direction to start excelling again. So, that's kind of a time management thing when it comes to homework, where if you are working on something, you just can't figure it out and you're really not making progress on your own, you need to get a nudge in the right direction so you can start making progress again. But this all goes towards this fictitious, let's say, number of 10,000 hours. Where in 10,000 hours, if you divide that up by the number of hours, waking hours in a year, it's a while. It takes a long time to get to that. Now, chances are you probably want to make if we're don't measure success by money for starters, but that you're going to get out of school, you're going to go get a job, whatever it is, you probably want to be as successful as you possibly can, as young as you possibly can. which translates into being a master of your subject area as young as you can, as early as you can, which means spending a lot of time in your focus area today. Now, having said that, now we can say, well, do you probably spend more time in this class than you do in other CS classes? Potentially. So depending on what the class is, I might make the argument that that class isn't hard enough. They're not challenging you enough. That you need to be doing more practice outside of class to become a master in that subject. Could also be an interest thing if you're taking a CS class on, let's say animation. It's not that animation is, bad, but it might not be your interest area. It might not be your cup of tea. Therefore, you might choose to do the bare minimum and you don't really care about the 10,000 hours for that. That's okay. But wherever your vocation lies, wherever you're going to be, embrace the amount of work that you have to do as long as it's constructive time, because that's adding up to this 10,000 hours, which will add up to mastery, which will ultimately add up to success in however you measure it. Whether that's in a paycheck, whether that's in, inventing something amazing and being the next pick your hero in the technology world, whatever it is. This is part of your future that we're talking about here, and I don't believe in busy work. So hopefully you never find that I give you an assignment that is truly busy work. Sometimes it might feel like it's busy work while you're doing it because you're not making progress on it, but hopefully when you come and you see the solution, you realize that, oh, I overthought that. That should be kind of a pretty common theme in Littman classes, is that you overthought a problem. Because what are we really learning? And if you go back to 150, what does Dr. Locklear teach that computer science is?
Problem solving.
It's problem solving, right? What's the first step of solving a problem? Go ahead. Understanding the problem. Okay. Was that just made up crap that was on a slide?
No.
I think we're going to see today that most of us didn't understand the problem that we were trying to solve before we started trying to solve the problem. Okay, show of hands. How many of you know how to count? Interestingly, for the Ann Arbor people here, we didn't get 100% buy-in. It feels like a trap. All right, so let's start looking at that. But does everybody...
Plug before we move on. If you want a nice boost onto the 10,000 hours, go to hackathons.
Well, that's true. But engage in the hackathons. Don't just sit in the corner and do nothing. But, does everybody understand this slide here? When I give you a lot of work, or, some people said, I require a lot of stuff outside of class, that's fine. Fair enough, I do. Because if I didn't require, you wouldn't show up. I'm doing you a favor. In 15 years, you're going to come back and say, not that every tech talk is, this life-changing event for you or something like that, but you wouldn't even give it a chance, most of you, if I didn't require you to go to it, right? Some of you would. The best students, or the people that really want to get maximum value out of their tuition, are going to take every little opportunity they can outside the classroom. But in general, students don't show up to things unless they have to, unless there's a grade attached to it, which is fine. I could attach a grade to it. And you could hate me for it. I don't care. I'm not going to lose sleep over that, because I know I'm doing you a service, right? Now, sometimes I feel bad. Sometimes I might say, hey, we're going to require something. It turns out to be like a dud. It's like, well, that was really kind of a waste of time. But if for every 10 things we do, 8 of them are pretty solid, it's probably worth continuing to do it, is, I guess, my view on things. But I just wanted to put some of that in context. That doesn't mean that they're bad complaints or bad constructive criticism. I just wanted to give you a rationale for why I give a lot of homework, but then I also come to class and make sure you see that it can be solved. You get to see both sides of that equation, and I think that there's value in that, at least for some people. We're not going to make everybody happy all the time, but that's the part of the rationale for, and it's just the nature of the class. This is a very much a critical thinking class, and you are really practicing something. It's almost like the full circle thing. This is like a senior level class, and you're practicing something that you learned in your first 20 minutes on campus, right? In 150, it's probably a lecture week 1, right? Solving problems, whatever, okay? We cannot solve any problem unless we understand the problem. And today's problem was to count. Right?
Mhm.
Most of us thought we already could count, right? All right, so before we even look at scheme, now, if you had to pick your favorite base to count in, most of us would pick base 10, right?
I don't know. I'm kind of
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's our base that we're most comfortable with, right?
Gotta be honest, you said base and I immediately put binary. Now I'm like,
Okay, we recognize that there's multiple bases, right?
yes.
So computers are ultimately speak base 2, zeros and ones. Octal's pretty popular as well, base 8. Hexadecimal's very popular, which is the example the book used, base 16. But for humans, we like base 10, 10 fingers, 10 toes, right? Good for us to count. Count, right? We're learning how to count today. You know, in a 400 level college class, we're learning how to count. All right, so.
And the homework was fun.
All right, so we're going to assume, remember, our goal here is to understand the problem and then understand a solution to the problem before we go and turn that solution into code. Make sense? So remind me real quick for the assignment, the number 10 in Bigits is represented like that, correct?
Yes.
That would be the decimal number 10 in Bigits with the ones place all the way at the left. So it's the reverse representation. Okay. So we'll start off with the smallest value, right? And then a 0, we add 1 to that. Let's just think about successor for a few minutes. We add 1, we get a 1.
Mm-hmm.
Okay. Then we add some stuff, ... We ultimately get a 9.
Mm-hmm.
Okay. What happens when we add 1 to a 9?
To add another decimal. Digit.
We need another digit because that's how math works, right? That's how decimal numbers work. So when I add 1 to 9, I get a 10. When I then divide it by 10 and look at the remainder, I get a 0. What does that mean? It means I ran out of space in this particular slot, right? So once we get to 9, we have a 10, but we don't represent it as a 10. What we actually do is we are going to take a 0 and we are going to add it on to the successor of the next guy over, which is a 1. So let me ask you this. If we had a baseline, so we have this empty list, we could say the successor of an empty list is a 1.
Mm-hmm.
Is that a fair enough assessment? So if I had a 9, could I cons a 0 onto the successor of the empty list?
Oh,
Yeah. Would that be good?
wouldn't that be? Yeah.
And what would that give me? That would give me a 0 cons onto a 1. Now, if I add 1 onto that, we have 0 plus 1, that's an 11, 12, 13, so on and so forth. Finally, we get to a 9. When we get to a 9, what do? 9 plus 1 is 10. 10 divided by n, in this case 10, has a remainder of 0. What does that mean we should do? We should cons a 0 onto the successor of the cooter, which is the Bigit 1. So that gives me a 2 there. So that would be a 0, 2, or a 20. Right?
Yeah.
Counting. Counting.
Counting.
Counting.
We should go back to kindergarten.
Okay, now, hold on. How many of you solved it this way? Okay, 1.5 people. Well, hold on. That's not a surprise who rose their hand, right? That's okay. There's nothing wrong with that. We're working towards getting all of us to be critical thinkers. And almost always, as problem solvers, humans in general, we try to overcomplicate problems initially pretty often, right? Even problems that are outside of computer science. Almost always, the computer science problems, they turn out to be way easier than they seemed when we first started looking at it, right? But human beings, we tend to overcomplicate problems. Why do you think that is? Why do you think we overcomplicate problems? Well, there's probably a truth to that. What's our tendency? Tendency is human beings, and we'll say stereotypically, the tendency for guys, right? That's what they say. So we just start solving problems. We just get out the power tools and just start doing it before we even know what we're doing. Before you know it, we've drilled holes through walls, we've done all this stuff, and we're not even... I can give you so many examples of times that I was like running like a cable in a house or something like that, and I drilled a hole through like the completely wrong wall just because I didn't even think about it. I was like, well, this is where it is. Then you realize that you're not all that great with directions inside of a house, even in your own house. Okay, I find when I'm on the main floor of my house, or actually if I go to the basement of my house and I'm standing next to like the water heater, and I think about what's above me, I'm going to call it a 25% chance I'm right. But what's interesting is my wife is almost always right. She has the sense of what part of the house are we standing in. I lose track, right? Out of sight, out of mind. So we have different, but I'll just start drilling, right?
So you said your wife works from home, right?
Well, she does, but she doesn't go to the basement very often. She actually works on the 3rd floor, so her knowledge of the main floor should be suspect. Okay. But the point is that before I should start drilling holes in the ceiling of the basement or the floor of the kitchen, let's say, okay, well, what I thought was the kitchen, but is actually through stone tile in the bathroom, which cracks, by the way, okay, especially when you don't let the drill bit do its job. Instead, you really push. Right? All right, so now fine, I just described, as you might have guessed, that was a very specific example, right? so clearly not something I've experienced personally. Okay. But human beings tend to approach problems like that. We're overconfident in our understanding of the solution that we tend to just dive into it. It's a tendency that human beings have. And a lot of times, we can get away with it. This goes back to the 200 class, because we're really, really, really good at solving problems. But sometimes, like a problem like this, we shoot ourselves in the foot. We're like, I know how to count. No, you didn't. You never actually thought about how you count. You just knew that you could count. Make sense? All right, so let's implement counting. For starters, we need to create a way of converting numbers. So I want to be able to take like the alphabet. I'll just stop it there for the screen here instead of going the whole alphabet. Actually, I'm going to have to do the whole thing. All right. I'm going to copy this in a minute, so that's why I just did the whole thing. All right, so that's my whole alphabet, right? We want to be able to say, give me the element that lives at bucket 6, for example. So if we're putting this in our Java terms, things that are familiar to us, we want to get char at 6 and have that give us a 6. We want to get char at 15 and have it give us an F. That's an ability we'd like to have here, right? That way we can represent our Bigits with the correct, let's call it character set for whatever the base is. We're counting in base 10 for our basic algorithm because that's what's most comfortable for us. But then we're going to be able to just change n to whatever we want. And as long as we're always doing, I mean, if I'm operating only through 0 and 9, which is the vocabulary of base 10, right? If I say, give me the character at 6, I get a 6. Give me the character at 9, I get a 9. Give me the character at 0, I get a 0. It works, right? It was kind of a unnecessary mapping. I didn't have to go from 6 to 6. But if I bump n up to something that has now a larger vocabulary of characters, and I say, okay, well, I want an 11, I need it to be able to get me that b, the character representation of that guy. All right, so I kind of need something like charat, and then I also need something like index of, where if I give it an a, it'll give me a 10. If I give it a 5, it'll give me a 5. Make sense? Those two tools would be beneficial for me to have for doing the converting between the number 11 and a b, the number 8 and an 8. All right, so we're going to write that little piece first, just so we make sure, you know, we have to run to Home Depot real quick and get our supplies. All right, so I'm going to steal this dude here.
Let's go Home Depot.
Where's my
Over by Android Studio.
Ninja? All right, there we go. All right, so for our initial example here, I'm going to keep n as 10. That's going to be the base we're going to be working with. And we're going to define vocab to be a list containing Ninja. A list containing the whole alphabet. And except I need one more closing parenthesis there. Okay. All right. So now let's go ahead and let's just name those functions that we're already comfortable with in Java. All right. So what is index of going to do? Index of is going to search vocab for us. We could pass it the variables if we want, but it's going to search vocab and it's going to give us the position within vocab where it finds the character we're looking for. Okay, so we're going to say define index of to be a lambda that takes in a, let's call it a list, let's call it a current pause. We'll say starting position. In fact, let's call that start pause. And search term. Symbol, something like that. All right. And what we're going to do is we're going to go through this list, starting at whatever this is. Presumably, we would pass a 0 in. We want to start at bucket 0. We look at the car. Is, you know, maybe we're looking for a 4. Is the car of this list, is a 0 a 4? No. Call it again. Add 1. Is the car of the list a 4? No. Add 1. Call it again. So on and so forth. So we'll ask the question, if, I'm going to use EQ like this because we're also going to be comparing symbols. If EQ car LST, if that guy is equal to our search term, if we found the guy we're looking for, we're going to return start pause. else, what are we going to do? We're going to add you know what? We can actually do this without start pause. Start pause would let us look for it somewhere in the middle. I already started writing it this way. We'll just keep going. So what I'm going to do is I'm going to call index of, passing it plus start pause 1, and passing it, I need to pass it the list first. So I'm going to pass it the cooter of my list. I'm going to pass it 1 greater than start pause 1 because we're going to be technically looking at the next bucket. And then I'm going to be passing it my same search term. And eventually we'll find it and boil down to whatever start pause was. So if I call index of on vocab saying start searching at bucket 0, whatever, and I'm looking for a 6, that should give me a 6. Oh, thank you. I was testing you, and Blaine, you failed me again.
I wasn't listening.
V had to back you up. Okay, so index of a 6 in vocab starting at bucket 0 is a 6. Index of A, I think I'll have to quote that like that, is going to give me a 10. All right, so this guy does what he needs to do. All right, and I could have written this a little differently. I did, instead of passing in start pause, I could have just done this as a string of adds. Add 1, 2, whatever is returned by the rest of the thing, but you know, and then ultimately boil down to a 0 here. So we just get a whole sum. We sum a bunch of 1s together until we finally get to a 0, but this is the way I wrote it, so we'll just roll with it. You know, we got the, you know, there was a couple different brands at Home Depot. This is the one we came home with. This is what we ended up with. All right. Yeah, this is the generic brand that, you know, it was made of plastic instead of the... I would, in general, I would say this is probably... This one is better if you want to be able to start your search at different places in there. The other one is probably recursively cooler, but whatever. So we'll say char at. This guy's going to be a lambda. We're going to take in a list, and we're looking for a search term. So here, I'll write this one the other way, kind of in the mentality of the other way. So I'm looking in this list for a search term, and I'm trying to get the character. Actually, for this one, I'm going to need the start pause. All right, so I'm char at. I'm looking in. I'm going to this position. We're not doing a search term. We're trying to get pause in this list. So we'll ask the question, if equal pause 0, then return the car of the list. Otherwise call char at on the cooter of the list and minus pause 1. So if I say char at, and I pass it, what's it called? Vocab? Vocab, and I'm looking for element 10 that should give me an A. Oh, I still had that other one down here. So that gave me my A. If I'm looking for element 4, this should give me a 4. All right, so far so good. So we got these two little tools we picked up from Home Depot that allows us to do those mappings. We wouldn't have needed these mappings if we would have said our maximum n is 10. But given that the book used 16 as their example n, we need the mapping thing. Okay, not to be confused with the map function. We're just going from, this is a 0 that's at bucket 0. This is a 1 that's at bucket 1. This is a 9 that's at bucket 9. This is an A that's at bucket 10. This is an F that's at bucket 15. Makes sense? That's how the bases kind of work. And we support n all the way up to 36 in this particular case. Okay, so now we are supposed to write our constructors for this. So what was it? We're supposed to write a 0. So define 0 to be a lambda that takes in nothing. And what does this guy return? He returns the list 0.
Okay.
Wasn't that a 0? If you wanted in your language to represent it as the empty list, you could, but isn't that a 0? A Bigit 0 is always a 0? No matter what base you're in, right? What's a 0 in base 16? It's 0. What's a 0 in base 2? It's 0. What's a 0 in base 10? It's 0. So that's what 0 is in any n. Make sense? All right.
Cool. Curiosity, why define it as 0? Why not just hard code it as a list that contains?
Well, you could. This is just our constructor. Yeah. All right, what else are we supposed to write? We have successor, predecessor. Was there another one?
We're supposed to check if something was 0 or not.
Oh, so define 0 to be a lambda that takes a Bigit as a parameter. And what does this guy do? Well, you can do a couple different things. We can assume that a legal Bigit is always going to be a list. And the smallest Bigit always has a car. We can assume that that's a truth. Therefore, we can say if car Bigit is equal to 0. Now, that's not good enough because that would map us for anything no matter what the length is. And equal length Bigit is 1. So if my list length is 1 and the car of it is a 0, I must be dealing with a 0. Go ahead.
I think we have to rename 0 question mark because it's built into the language as a regular 0.
All right. Now, you could probably come up with some other ways of detecting a 0 or something, but if my 0 list looks like this, really what I'm saying, I mean, well, we could actually have done a EQV. I think we'll compare the list there. So we could have actually just said this. We could have said EQV Bigit and 0, like that. I think that will work as well. Oh, it's a question mark after EQV?
Yeah.
That. So we should be able to say 0 lol of, I'll just pass in 0 like this, and that should give us a true.
Do we have to call 0 in the equiv line?
Well, you shouldn't have to. So that's still false. So this needs to be equal. Actually, I don't think that has a question mark on it. Oh, maybe it does have a question mark on it. Well, we'll go back to my other solution. I can't compare a list directly to itself, to another list, with any of the EQs. Interesting. Thought I could compare the contents of a list.
Yeah, I thought equal specifically did that.
Yeah, that's what I thought too.
So if we, in the EQ line, if we just have 0, it's actually gonna spit out the lambda, correct? We have to call it with,
Oh, thank you.
Yeah.
But that's still, oh, we changed it to the 0 when I originally had the empty list there. I had the list 0, but I tried to do it with an EQV. I originally tried to do EQV on this, which gave us a false, but I didn't use the 0 constructor. I used just the hard-coded. But that guy is giving us a true there, so why didn't it? Because I think I originally did
we didn't have,
that.
I think that was part of the previous solution. Is it false?
Yeah, so this gave me false on this, but not false on 0.
Oh. All right, if you pat, okay.
It looks like EQV has to be 2 lists.
Yeah, and we are passing it.
Yeah, we are passing it 2 lists.
Well,
What does not
we'll
work?
see when we're calling it in 25, we're using the 0 constructor that we made. So we pass out a 0 list.
So I bet you this gives me a true. This is the list 0 versus the 0 constructor. But this is equal.
I think that's false. Oh, that's true. Okay. There we go. Full equal.
Yeah, but that still doesn't answer the other question.
So what is the difference between being and equal and
It's the type, it's how deep it compares the contents, but it still doesn't answer the question of that working for equal. That gives me a true, but this should also work for EQV.
it's just not deep enough.
Well,
Yeah.
we might say that's the case, but this did work for EQV,
Mhm.
which boils down to the list containing a 0.
But it does boil down to that. I don't know. Maybe it has to do with where it's actually looking first.
This right here,
Because it's looking at line 18 first, which does ultimately point to the 0 list, but
yeah, so maybe maybe it has to do with how it resolves that guy as a function, where this will look at the top level output. Oh, sorry, this should be a 0 in here, not the empty list. All right. So let's just call that good. Several different ways that will accomplish it, but it is interesting. At some point, we'll want to really investigate EQV versus equal versus EQ. Well, EQ is where symbols start. We'll just call it good for right now. Relatively unimportant for the assignment. That test to see if something is 0, and the original one I had up there that said, is the car a 0 and is it a 1 list? That would have accurately tested it.
And how about the equal sign? Would that do anything better?
That only works for numbers.
Oh, okay.
All right. So now we're needing to define successor. So define successor. This is going to be a lambda that takes a Bigit as a parameter, right? And the ones place is the far left. That's the car of that guy. So I'm going to ask a question about that. So I want to take the car of the list and I want to add 1 to it. And we could even do this in a let if we want to. So I can do it in a we talked about let star as well, right?
yeah.
We're going to have things in terms of each other. So we could say let star num, and we'll set num to the car of, we might not necessarily have a car of Bigit if we're ending on the empty list. So let's not use a let for this. We'll just do it. Let's call it the inefficient way. All right. So we're going to ask the question. We'll put a cond in here. If Bigit is the empty list, then we want to boil down to a 1, right? So equal, well, actually, we'll just say null Bigit 1. Okay, and we'll see why we chose it as a 1 here in a second. Otherwise, we want to look at the car of that list. So actually, maybe a if would have made more sense here than a con, because we really only have 2. No, con is fine. All right, so we're going to take the car of Bigit. We know that it must have a car if it's not the null list. Okay, and then what are we doing to the car of it? We're adding 1 to it, plus 1 car, and that's going to give us a number. What are we doing with that number? We are modding it by n. This is the number we maybe wanted to put into a let, but we'll just calculate it multiple times. Because if I have a 9, 9 divided by 10, looking at the remainder, how many times does 10 go into 9? 0 times. 10 goes into 9 0 times. Therefore, I don't have to carry it over to a new bit. Go back in here. So if I have 8 as my starting point, the successor of 8 is 8 plus 1, which is 9. 9 mod 10 is going to be a 0 remainder 9. Right? So that means that the 9 is good. We don't need to do anything else. That is our successor. The 9 there. I don't have to fix anything else. So what do? I cons the 9 onto that rest of my, the rest of my list. And I'm done. But let's say I had a 9 plus a 1, which gives me a 10. 10 mod 10, how many times does 10 go into 10? Is equal to 1 remainder 0. So if the remainder is a 0, that means that we have to reset this value to a 0 and then call the successor on the rest of the Bigit, the cooter of the Bigit. That makes sense? If we have a list that looks like this, we'll go up here. If I have an 8, I take the car of that, I add 1 to it. That's what I'm doing right here, right? Car, add 1. That gets me a 9. Then I'm going to mod it by 10, mod it by n. Where in my case here, n is 10. I'll mod it by 10, giving me a quotient and giving me a remainder. If the quotient is 0, then I'm just going to keep this value. But I need to make sure that I take this, the number that came out of this, so I need to make sure I take that 9 and I turn it into its numeric, actually when I do the math, when I concatenate something on, I need to make sure I do the mapping. I want to make sure I don't cons a 10 onto something. Because when I divide something by 16, let's say n is 16, my possible answers will be 0 to 15. Anything above 9, so I want to turn a 0 into a 0. I want to turn a 5 into a 5. I want to turn a 9 into a 9. I want to turn a 10 into an A. That's what I'll be consing on, is the A. When I take the car of it, so right now we're just making this work for base 10. Okay, so what I'm going to do is we're going to finish this for base 10, and then I'm going to give you the assignment again in this new thing. So if you already solved it the right way, then you can just resubmit it. But we're going to do this in terms of base 10 first, so I actually don't need to map it since I'm assuming base 10 for our base thing. But I'm giving you the tools to do the mapping. All right, so assuming base 10, we'll say we have a remainder of 9, so we have a remainder of something other than 0. What do we do with that? We car that onto the cooter. We cons that onto the cooter of the rest of it. That gives us our successor. So when I take that number, what is it, modulo n.
Oh, not you.
Oh, modulo. Okay. So I'm going to take the car plus 1. I'm going to mod it by 10. I'm going to say, is that guy equal to 0? What are you asking about? Okay, so I'm going to say if, when I take the modulo, it's equal to 0. We go back to this screen here. What happened when I had a remainder of 0? That means that I have to call successor on the rest of the list. So I will cons a 0 onto whatever is returned by successor on the cooter of Bigit. Go ahead.
So let me start this out real quick. I think I had this backwards in my head. Is successor supposed to increase the value
by 1
or decrease it?
Predecessor decreases, successor adds 1.
Okay.
All right. So this is what we do if we have no remainder. That means that we go into it an extra time. So I'll reset my current count and cons that onto the successor of the rest of my Bigit, which is a Bigit in and of itself. Otherwise, if there is a remainder, what am I going to do? I will cons, just steal that number for right now, that guy onto the cooter of Bigit. Oh yeah, because I'm in a cons. Thank you. Or I'm in a cond. This guy, finish that off. There we go. Else. Will cons 1 greater than the car onto whatever the rest of it was. So we should be able to say, define, well, here, we should be able to say something like successor of 0, and that gives us a 1. We should be able to say the successor of the successor of 0, and that gives us a 2. We should be able to, I'm going to cheat here. I think it's going to look like that. Is there something different about the way I'm representing? There seems to be something different because, I mean, the way I'm doing my numbers, I must not be building lists right, or I'm in the wrong language here. So let me just define a function called count, and this guy is going to be a lambda, I don't know, num, and this guy is going to say if equal num 0. We'll call this guy Bigit. Then we're just going to return Bigit. Else, we're going to call count on minus num1 and successor of Bigit. That should allow us to call count to 12 on a 0. Function call after the parentheses.
The 12.
Oh, hold on. I'm just calling it wrong. Count takes in a 12 and takes in a function. There we go. So the successor of second argument must be a list, but received a 0 and a 1.
Oh, from the null statement, maybe?
Oh. Yeah, the nulls are boiling down to a 1, so this should boil down to the list 1 conjugate onto that. It's the Bigit 1. So this is a 12. Count to 12. Count to 43. Gives me a 43. Count to 743. This gives me a 743 as a Bigit. See how that's working? All right, so for next class, I'll give you all this code as a starting point. Finish making this work for n equals 10 as a starting point. But it should work for all the other bases, but I can promise you if you make it work for n equals 16, it'll work for everything. Because you will need to use our index of and our char at for doing the mappings. Make sense? So same questions you had due for today, but if you didn't already do it this way, do it this way. You know, in a recursive definition in terms of predecessor and successor. If you did already do it this way, just submit it, then because you already understand the concept. Questions, comments, concerns, bribes. All right, so we're learning how to count. All right.